So welcome back to particle physics and the standard model. This is lecture 31. And in the last class, we saw what we really meant by an adjoint representation and where this notion of the number of gauge bosons being equal to the number of generators came from, right. So we defined it a bit formally. And in particular we saw that adjoint representation is when you have the transformations of the group elements in the vector space inhabited by the generators themselves. This might look a little bit confusing. If it is, then don't worry about it. What we really need is how the gauge field itself transforms. Okay, in the adjoint representation, this is how you want the group elements to transform, the gauge fields in this case, and it is this interplay between the adjoint transformation and the fundamental transformation that gives rise to covariant derivatives and from there on to gauge invariant theories. And we also saw one consequence of having this entire structure of the non-abelian structure, which is that the first step of that consequence is you got vertices like these, 3 gluon and 4 gluon vertices, or 3W and 4W boson vertices, and from there we saw where asymptotic freedom came from, okay, in an intuitive way. Okay, the actual calculation involves a lot more field theory, but at least in an intuitive cartoon way we can understand where asymptotic freedom comes from, namely that when you have electromagnetism you only have screening coming from the vacuum polarization due to diagrams like these where you split off a fermion and antifermion, but when you have non-abelian theories, because of these extra vertices, you also have vacuum polarization where you split off the field itself, the gluon in this case, okay, the gluon itself is being split off, because of which you have, in addition to screening, you also have an anti-screening effect which basically enhances the field for a distant observer, okay, and there is a competition between what the color charges and the number of flavors that you have. We found that we are living in a world where indeed you can get an asymptotically free theory because we have less than 16 flavors. Okay. One thing I touched upon in the end of the last lecture is that we talked about a universal coupling in the gauge, right. So where does this universal coupling enter? Over here, for instance, right. When we write the gauge transformation, I just slyly introduce this G, right. Earlier also in QED, we had something like a G. Remember what that was? That was what we called an E, the QED coupling, right. So what I mean by universal is that, where else have we written this? See over here, right. In the field strength tensor itself, you have a coupling sitting around, and that is a coupling that gives you the interaction, that determines the interaction between the A fields, which are gluons or W bosons and so on, right. And notice that that is also the coupling that determines the interaction between the photon, sorry, not the photon, the gluon or the W boson and the corresponding fermion. Agreed, because it's in the covariant derivative, right. See, this coupling keeps coming up again and again, right. So because it is allowed by the structure, you cannot help but writing it down, and that is exactly what determines the interaction strength of that theory. Okay, in other words, G is a unique for every let me call it a GI, okay, a unique coupling for the group which I am going to label by I, okay. So for SU3 color we call it the strong coupling is also called G3 sometimes, and for SU2W we call it G2, some people call it GW, G bar to etc etc. Okay, and this coupling is one of the free parameters of the standard model. There is no way to predict this coupling from first principles. Okay, so this is literally obtained from measurement. Okay, and the reason the strong force is called the strong force and the weak force is called the weak force is simply that the strong force coupling happens to be much larger than the weak force coupling. That's all. Okay, this is around order 0.1 and this is order 1 basically. Okay, this is literally where we get these concepts. Okay, whether there is asymptotic freedom or not, etc., none of that matters for defining strong versus weak. Okay, so okay, excellent. Now we are ready to write down a generic Lagrangian. I'm going to call it a theory of spinors. Okay, invariant under a local SUN. Okay, how would that look like? Because it's non-abelian, let me just put it that way. There may be other terms, but I'm just going to write the kinetic term of the gauge field and the kinetic term of the spinor field itself. Okay, there's an I here, gamma mu to mu plus here comes the universal coupling of the SU2 A mu T A T I J A. What is TIG? Those are the generators. Okay, and there's a mass term which you cannot miss and a phi j, psi j. Agreed, this is the most general Lagrangian that you can write down when I have n different fields transforming under an SUN. Agreed? Notice that in the kinetic term I need to have a delta function because I need to actually multiply the exact field with itself. That is also true in the mass term, okay, but not true in the interaction term. That's why I have just a TIG. Okay, the generators can basically marry off two different degrees of freedom that are transforming in the SUN. Okay, excellent. So this is what once again I'm going to write this. This is where I get 3 colors for SU3. Why? Because IJ run from 1, 2, 3, right? And for the weak force, sorry, SU2, I get 2. People don't generally give these names, but we might call them isospins. We also call them flavors. Okay, although there are 6 flavors, even the up and down are distinguished by calling them flavors, right? Okay. One other thing we need to decide on before we write down the standard model Lagrangian is field strength tensor notation. because we don't want to keep writing F nu nu for all the field strengths. Okay. So might as well call the SU3 field strength, I'm going to call it G mu nu, not F mu nu. Okay. And then the SU2, that I'm going to call, what do you think is an intuitive notation for that? W mu nu. So it should be clear what this is, right? This is for the gluon, that's why it's a G. This is for the W boson, right? What other group is there in the Standard Model? It's not electromagnetism, that will come later. The Standard Model as such is composed of another abelian group that we call hypercharge. And for the hypercharge, we write the field strength tensor as B mu nu. Okay. So I don't know why it's called the B boson. I know why it's called a W boson. It probably has to do with Weinberg having come up with that. But for the hypercharge, it's the B boson. Okay. Okay. So that's the gauge boson content or the gauge content of the Standard Model. What about the fermion content? Okay. So of the SM. Okay. So here is a notation I'm going to use in the rest of the course. So this part is important. Okay, I'm going to list the 5 fermions, but on the other side of a table, I'm going to write down how each field transforms under each of these groups, and I'm going to write that as a direct product. What does that mean? It's not a direct sum, because this is not some reducible representation or anything like that. I'm going to write the representation in which each of these fields lives in for each of these groups. Okay, if it transforms under all 3 of them, so be it. That's what the direct product means. Okay, remember we saw this already when we broke down the Lorentz group into the 2 SU2s, we wrote a direct product there, right? Okay, so what is the first field? It is a capital Q. Okay, you can call this a quark, but better to just call it the Q field. Okay, and why is there an L? We'll see in a second. The notation I'm going to use is, it is in the fundamental representation of the SU3, which I'm going to denote with a 3. Okay, comma, it's also in the fundamental representation of SU2. So it's a doublet under SU2. It's a triplet under SU3 and a doublet under SU2. That's what we mean by this notation. Hence this. Okay, and finally, the last one I'm going to write with a different color, because this, so maybe this also I should have written in a different color, okay? Because this is not a representation, this is just the charge actually, okay? That's just the hypercharge. So let me, only in this instance I'm going to write, that is basically the value of Y, which is a hypercharge, which is also, just like electromagnetism, it is a charge under local transformations, local phase rotations. Okay. Now, can you see why there's an L here? Because this field is charged under SU2, the weak force, and the weak force acts only on left-handed objects, right? So that is what we're denoting with an L. To make sure, from just the notation, you know that it is charged under the SU2. Okay. Next, I have a UR. Now since I wrote an R, you can already guess what I should write in the second column. That's just a 1. That just means this is a singlet under SU2. Okay, that is, it is, since it's right handed, it is not charged under the weak SU2. Okay, sometimes I'll just use the word weak force to denote the SU2 here, not the electroweak force. Okay, this is just the weak force. Okay, what is it under SU3? Of course, this is also a triplet. Okay, and it turns out that the charge I have to assign is 4/3. Okay, we'll see soon what there is a relation between charge and isospin that we'll see from between electric charge and isospin. Okay, so these are all reverse engineered values for these things based on the electric charge that we see. Okay, what else? Is there any other kind of quark? There's a down quark which is right handed. Okay, since it's a quark, it is also charged as a triplet under SU3. It is also a singlet under the SU2, and I'm going to assign a charge, a hypercharge of -2/3. Okay. Next, what other fermions do I have? So I have leptons, right? So is the lepton charged under SU3? Of course not. That's exactly what makes it a lepton. But this, since I've given it a subscript L, it means it's a left-handed object, and that should mean it's a doublet under SU2, and I'm going to give it a hypercharge of -1. Okay, and to round up, I have a right-handed field. You can call it an electron field. It also being a lepton is not charged under the SU3. It is not charged under the SU2 either because it is right-handed. And finally, I'm going to give it a hypercharge of -2. Okay, that's it. This is the fermion content of the standard model. Okay, the fundamental in the fundamental representation, these are all the fermions that we have. Okay, so this is easy to remember, right? Just remember Quidel. Okay, it's easy to pronounce. So QUDLE. Okay, and sometimes, in my opinion, confusingly, people write this out as a UL under DL. Okay, and similarly this LL, people write this out as a neutrino under electron field. Okay, you can, but there is no need to do it right away. Why? Because at this stage you don't yet know what is the composition of QL and LL. Okay, this notation only makes sense after you break the symmetry in some way and get electromagnetism out of it. Then I can think of a neutrino without a charge, I can think of the up and down quark making up the capital Q and so on. But right now, all you need to know is that this is a doublet under SU2, that's it. Okay, I could have just called it, if I want to write it as a doublet, I might as well call it QL1, QL2. That's good enough at this point. Okay, just remember this. Similarly, I could have called this LL1 and LL2. Okay. Later we can assign meanings to what LL1 and LL2 are when we do symmetry breaking. Okay. Again, one point I want to make here is that the strong interactions, right, could also have acted on just the left-handed spinners, right, or just the right-handed spinners. There's absolutely nothing a priori that forbade the strong force to do this, right? But it didn't. Okay, and similarly, the weak interactions could have done the same, and they did, right? So interaction, and it did, right? Remember why? Because when you broke down the SO3 into these two, this is a Lorentz group, right? The left-handed and right-handed SU2s, they both were independent representations of the Lorentz group, correct? Under which you charge the spinners, right? So absolutely you could have charged only the left-handed or the right-handed ones with some interaction. As far as the strong interactions go, it didn't do that. It charged both the left-handed and the right-handed fields under itself, whereas the weak interactions made use of this option, and only the left-handed fields were charged. Okay, so there is no very big mystery here for why only left-handed particles feel the weak force. Why is there maximal parity violation in the weak force? Okay. Okay, excellent. So I'm going to represent what I've written in the table in terms of some vertices now. Okay. So that the meaning is really, really clear. It just means that for the strong force, okay, I have charged the QL fields and the UR and the DR. Okay. The weak force, let me pick orange. The weak force acts on the QLs, so I can have this interaction, I can have this vertex coming from its own non-abelian Lagrangian, doesn't act on this, doesn't act on this, it does act on the LL, okay, and that's it, doesn't act on ER either, okay. And finally the B force, right, the hypercharge acts on all of them, that's what we've written, everything is charged under that hypercharge, right. So I can have this vertex, I can absolutely have this vertex for DR and for the LL absolutely, and finally for the ER as well. Notice that the ER is charged only under the hypercharge. Okay, good. Finally, are we missing something here? Something very important when we list out the menu of fermions making up the Standard Model? What we are missing is the 3 generations. Remember the flavor problem. Why are there 3 generations of matter? Right? So I could have absolutely started out by putting indices all over the place and just saying that the I stands for a generation index. So I have up quark, charm quark, top quark for QL on, for all the QL, UR and DR. And similarly, I would have electron, muon and tauon, correct? For the leptons. Okay, that is indeed the matter content of the standard model. Let us now look at really what interactions these objects have. Okay. So, what are the first interactions I can write down? I can write down the gauge interactions. And how do I do that? I need to make use of covariant derivatives which give me the kinetic terms of these spinors, right? So I can write this now in one shot, right? Because we already know how to do it for a generic theory, right? We've just built up all the ingredients. So I'm going to write the whole thing in one shot, putting in all the interactions possible. Okay. So let me do it for the QL term, okay, because that participates in everything, right? So the standard model Lagrangian absolutely contains okay, this is the kinetic term, the literal kinetic term, but in the covariant derivative I'm also going to have what? It participates in the strong force, so I have the strong coupling and it hits all the 8 gluons, right? What else? I have the weak coupling and that hits all the 3 W bosons. And notice that for the strong coupling I have written a TA, which is what I denote as the Gell-Mann matrices, okay, the generators of the SU3. When I write tau A, I am talking about Pauli matrices divided by 2, the generators of the SU2, okay. And finally there is a gauge coupling which we did not introduce before, so I am doing it here. There is absolutely a unique gauge coupling for the hypercharge as well. So I have the B boson, and remember we had a Q in front when we wrote QED. Instead of Q, I am going to write YQ. That's the hypercharge, okay. And I am going to write another Q, don't get confused. This Q is the quark field, okay. And in this case, what did you decide was YQ 1/3, right? So I'll just write that down with YQ equals 1/3. So this is how we write the entire covariant derivative. You just put in all the fields, sorry, all the interactions that it takes part in to construct the covariant derivative, okay. So I leave you to construct the covariant derivative for the other 4 fields also, okay. That should be trivial, right? I've written down the hardest one where the Q is the one that QL is the one that participates in all 3 interactions. So I've written that down, okay. Very good. Now we get to something very interesting, which is to think about the masses of these particles, okay. If you think about it, I've written down the kinetic term, using covariant derivatives. So I've written down all the interactions. I've accounted for all the vertices that I've drawn here. But what about the masses? Where are the fermion masses here? Okay. That's going to be the theme of the next 2 or 3 lectures. Okay. What about fermion masses? Okay, so I'm going to say something about this and wrap up the lecture. and in the next lecture we will take up really what's going on with this. Okay. See the reason we didn't write a fermion mass is that it is literally 0 at this point. Why is that? Because if I were to write this in 2 spinner notation, right, fermion mass, right, so how would this be? So it should look like mass of the fermion. Remember, in 2 spinner notation, I had to marry a left-handed field with a right-handed field, correct? And similarly, for the U also, right, I had to marry these 2 chiralities, correct? From all those lectures ago when we introduced spinners, right? Remember this in 2 spinner notation. Right? But I am not allowed to do this now, right? Why? Because my left-handed fields are charged under SU2, right? The right-handed fields are not. So what has happened is, this is not gauge invariant, right? The SU2 index will be hanging around here, right? So in particular, under the SU2, the weak force. Do you agree? So gauge invariance has imposed this non-chiral structure on me, that the chiral structure on me, that I need to have massless spinner so that the left-handed and the right-handed components actually can transform independently. That's what we are seeing here already, right? I just wrote down a Lagrangian explicitly for left-handed fields, right? So put differently, the gauge invariance, okay, of SU2W forbids fermion masses or fermion mass terms. Okay, so necessarily we are living in a massless theory. Okay, and in the next lecture we will see how even the gauge bosons are massless at this point. That is also imposed by gauge invariance. We already saw this when we did QED, but we will see this in more detail, and from there we will see how really we can actually give masses to all these fields, the gauge bosons and the fermions. Okay, something intricate is going on here, right? Alright, so I will stop here. We will take this up in the next lecture. Thanks.